Okay, so in this lecture we're going to do a bit of an introduction to curve fitting and mathematical modeling. Okay, so we need to, first of all, we need kind of the language of functions, because what we're going to be doing typically is we're going to have two variables here. One is going to be what's called a function of the other one, and the way you're going to probably want to think about that is one of them depends on the other one, and usually it'll be y depending on x. It's just convention that so one of them's called the independent, the other is the dependent. Basically the thing that's independent is the one you control, and the one y is the one you measure. Okay. So in engineering, the way to think about it is to imagine a function as a relationship between variables. This is what we said. We can write something like y equal to f of x. This y is a function of x, y depends on x, or even y is equal to y of x. This y of x would be the value of y say y of 4 would be the value of y when x is equal to 4. As an example, the area of a square is a function of its side length. The area of a square depends on its side length, and say when the side length is 4, the area will be a of 4, which is 16. We can visually represent functions using graphs, where we graph the y versus x, and all of the points on the graph are of the form x f of x. And you can think of the x as being the input and the y as being the output, so they're all of the form input output, because remember the y is the f of x. Some of the functions will be of the form y is equal to f of x. Now actually all of them are, and this just means that y depends on x, but it might also be that there's a formula here that you feed in the input x and you get out the output. Okay, and later on you'll see functions that depend on more than one number. They're called functions of several variables. So as an example here, the area of a square. So you got the area depends on the side length. Now, as I said, usually you control the x variable, while perhaps you measure and record the y variable. But the big thing here is that all the points on the curve are of the form input, output, x, y. So for example, if the side length is 0, the area is 0. If the side length is 1, the area is 1 squared, which is 1. If the side length is 2, the area is 4. If the side length is 3, the area is 9. Now realistically, we kind of need to do this for all possible values. So for example, if the side length is square root of 2, the area is square root of 2 squared, which is 2. And essentially we have all these points included here. And you take all those points for all the possible inputs. This is called the graph of the function. And every single point is of the form input output. So for example, if I go across from 5 here, square root of 5 in, 5 out, input output. Okay, so some examples that we might see. The unit cost of training a new trainee depends on the number of trainees. So this is kind of the idea. Suppose it's September, or say it's December, and say Pennies or whatever is training people to be new workers. It'll cost a certain amount to train one person. Now once you have one person in training, it'll cost a bit more to add in the second person. But adding in the second person is a lot cheaper than if you already have 15 and you're training one more. This is this unit cost. It might be called the marginal cost as well. So once you have the number of trainees, you have the marginal cost depends on that. The temperature of a component depends on the time it has been used. The longer, the larger T is, maybe the larger the temperature is. The depth of a pile driving, so how deep this goes, depends on how many times it's already gone. So on the first one it'll go a certain depth, on the second it'll go a bit deeper, on the third it'll go a bit deeper, and then maybe after a while it'll slow down. The yearly sales of a product depend on the number of years the product has been on the market. Now you wouldn't think here, like some of these it feels like the x is kind of causing the y. So here the blows are causing the depth, the time is causing the temperature. Here it's not really like that, but everything else is there. Like really the one thing you definitely need is that for each value of the input there is only one output. Like if you take a particular, say after 3 years, the yearly sales is one number. There's not a few of them. And then the big one for us in chapter 2 for beams, the load per unit length W, the shearing force, the bending moment, the slope of the beam, the deflection of the beam, all depend on the distance from one end of the beam. So now again, it's not like the distance from the end of the beam causes, say, deflection, but as you go, say, 1 meter along the beam, there is one number that describes the deflection at that point. So these are all functions. What have we got here? So very often data is collected and the relationship between the sets of data is not known. So for example, so the temperature of an object could be measured, but there might not be any known formula for this. I think what we're getting into is why are we looking at curve fitting? So curve fitting is going to be, you have some data, you want to find the equation of this. Now it doesn't necessarily have to go through all the points, as we'll talk about a bit later. That mightn't actually be good, especially if measurements have errors. So here's an abstract example. So the independent variable x, for each value, so 0, 1, 2, 3, 4, we measured and recorded y. So two questions here would be interpolation, which is asking the question, what is going on at 2.5? If this is our data, what is our best understanding of what the y value is at 2.5? That's called interpolation. What about at x equal to 5? So given this evidence as such, what is our best guess for what's going on at x equal to 5? That's called extrapolation. There's other things that can go on. There's various different things, and actually I think we're going to see them in examples. Okay, so this is one example, interpolation, extrapolation. We'll give another example. Another example is where you actually do know the relationship between the variables y and x, but they depend on some constants. So for example, maybe if you look at, if you take a length of metal and you stretch it with a certain force, so you have the initial length of the metal, stretch it, and then you've got the subsequent length. So what you could do is take different lengths of the metal, stretch them with the same force, and see what is the different, like plot maybe the stretch length versus the original length. And it turns out if you plot that in what's called the Hooke regime or something like that, it turns out that there's a constant involved in the relationship between them, which is the Young's modulus. So what I'm getting at here is there can be a theoretical relationship between variables, but you're missing something. But what you can do is you can do an experiment, plot the points, find the curve of best fit, and from the curve of best fit, find those constants. For example, doing what I'm talking about there is an experiment actually to measure the Young's modulus. So you can actually do measurement with curve fitting. So I got interpolation, extrapolation, and measurement. And there's another example or two, but we'll see it actually in we'll see it how we say in the examples. Okay, so that's the basic curve fitting.